Welcome everyone to another installment of our AARMS Scientific Machine Learning Seminar. It's a great pleasure to welcome Scott MacLachlan today from Memorial University, who will talk about the use of machine learning for the design of preconditions. Take it away, Scott.
All right. Thanks, Alex, and thanks everyone for coming. I'm going to talk today about sort of a few different things, and so I'll start by thanking, I guess this works out to be sort of 3 generations of collaborators in this work. I'm going to talk a little bit about some old work that comes out of my time as a PhD student and as a postdoc, work with my supervisors, Tom Antoifel, Steve McCormick, and Yusuf Saad. And then the new work, the real reason I'm here talking about this is work with my collaborators, Luke Olson and Matt West from the University of Illinois in Urbana-Champaign, and with 2 students. So Tarek Zaman is a student at Memorial here with me, and Ali Tagabakshi is a student in Illinois with Luke and Matt. And I'm really going to set up, I'm going to spend a good bit of this time setting up why we do the things we do, and then I'll talk about what Tarek and Ali have been up to in terms of using tools from machine learning or similar optimization approaches in this work. So I like to start with what is sometimes a very controversial statement here. I believe that the point of numerical simulation is to answer questions that are posed by scientists or engineers. And I know some of my colleagues disagree with that, but I really think that the whole point of doing scientific computing, scientific machine learning, numerical analysis, and these things is to answer questions that come from other domains. And so, the way that this often works is somebody poses a question. That question leads us to a mathematical model. The mathematical model might be in terms of differential equations or in terms of other sorts of things. That mathematical model becomes a discrete model that we put in a computer, and we do some sort of simulation. And that simulation spits out some sort of data that we use to answer the question. And of course, in a practical setting, it's not a straight path through this. We get partway into designing a mathematical model, and we go back to the engineer who posed the question to find out what's important and revise the model, do some simulation, go back and revise, and so on. But roughly, this is the path. And of course, my talk today is really going to be sort of focused on this numerical simulation stage. What do we do when we're actually trying to approximate solutions to complicated mathematical models in a computer? The mathematical models that motivate the sort of work that we're doing come from conservation principles. And so I know some of you are very familiar with this, but just in case you aren't, I'm just going to think about the basic conservation of something in a moving fluid. And so I'll say, think about a fluid that's moving through a domain and it has a velocity v, and there's some conserved quantities in that fluid. So you can think about conservation of mass or momentum or energy or these sorts of things. And L is going to denote here the density of the conserved quantity that we're interested in. And then I'm just going to draw some blob in the fluid flow domain, and I'm going to call it omega. So it's some control volume within the flow, and it has an outward unit normal vector n. And then if I just want to sort of first principles say, what does it mean for L to be a conserved quantity? I can write down this equation here that says that the time rate of change of the amount of L in domain omega is influenced by 2 factors. One of those is the flux of L across the boundary of omega. N is the outward unit normal, and so I get a minus sign on that flux because that's the outward flux. And then plus any sources and sinks of L, of mass or momentum or energy or whatever within the volume that I'm looking at. When I write it like this, it's not the most useful formula because I have a time derivative outside of this integral over volume. This is an integral over a surface, and I can't really compare these different things. But I can use, say, the Leibniz rule to bring in that time derivative. I can use the divergence theorem to rewrite this volume integral. And so I can write this in terms of, say, a single integral over the control volume omega, describing how L changes now pointwise within that omega. And then since that control volume was a completely arbitrary thing, I can write this down as a pointwise differential equation, a sort of hyperbolic conservation law that would be satisfied by conservation of L. And of course, maybe it's not conservation if I have sources and sinks represented by Q, but that sort of goes as a right-hand side term. And so, we apply this sort of a generic conservation law in many, many settings. And if I apply this, say, to conservation of mass and momentum, I assume an incompressible fluid, that means a constant density, and I assume a Newtonian fluid so that my viscous stress is linear in strain. That sort of gives me this sort of a diffusion term or a dissipation term. I get the classical Navier-Stokes equations. We do lots of work that sort of starts from the Navier-Stokes equations as a simple model. And we get to things like modeling, say, two-phase Navier-Stokes flow. So what happens, for example, if you have air bubbles in a industrial fluid and you want to understand what effect that has on the process that you're using the fluid for. Or we might look at, say, thermal flows. This is a sketch on the left-hand side of pushing molten aluminum through an extrusion die. Or in terms of geophysical processes, this is a sketch on the right of what's happening within the Earth's mantle, the convection that's generated by the heat from the Earth's core. All of these are modeled with some sort of PDEs that we can derive somewhere following this similar conservation law principle. Now that's our mathematical models, but in the end, we want to get these in a computer, so we need to have sort of discrete models that go with that. And there's, of course, a whole industry set up about how do we discretize these sorts of problems. And so you can think about temporal discretizations. These are time-dependent PDEs. Maybe you use Runge-Kutta methods, maybe you use split-step schemes, maybe you use BDF methods. And then spatial discretizations where you might look at finite difference or finite element or finite volume methods and so on, depending on the details of the flow situation you're interested in modeling. I'm not going to talk a whole lot about the specifics here. We're going to end up looking at some numerical results for finite difference and finite element discretizations of pieces of these bigger, more complicated sets of equations. Now, when I look at, say, that problem of modeling mantle convection or those industrial flow examples, these lead me to very large, typically nonlinear systems of equations that I need to solve, say, at every time step in a time-dependent simulation, or if it's a time-steady simulation, I need to sort of solve these things once to get me the data that I'm looking for out of my simulation. I'm just going to assume that the linearization's been done somehow reasonably, maybe a Picard iteration, maybe I'm using Newton's method. Maybe I have some sort of split step scheme where I'm using some explicit and some implicit aspects to my time integrator. And that takes me to the question that I really want to focus on today, which is just how do we solve a linear system AX equals B? And the good news here is I'm teaching linear algebra to first-year engineers, and so I'm really good at solving AX equals B right now, and Hamid's in the same boat. You use something like Gaussian elimination, right? This is sort of this recursive procedure that reduces you from, say, a dense matrix A, pictured over on the left here. Just imagine all these X's are some numbers you've thrown into the matrix, to its row echelon form, this upper triangular matrix on the right that we can use to do a back substitution to solve for all the variables in our system. So Gaussian elimination is great when you're in, first-year engineering and you're solving systems that are 3x3 or 4x4. If you look at the actual cost associated with this, for an n by n matrix, it gives us an order n cubed set of operations. Oh, I see a question. Is there a problem with WebEx? I'm on slide 8.
I see slide 8.
6.
I see slide 8.
Okay, so I've just got a problem in New Brunswick then. I'm only seeing slide 6.
I'm in New Brunswick. You are in a separate universe, a separate New Brunswick.
Don't understand it. Okay, so I'm sorry. I'll just try
Well, here, let me stop sharing and start sharing and see if
there it is. Yeah, okay.
resets your view. Is that better?
Yep. Sorry about that.
No worries. And now open that chat window again so that I see it if it happens again. All right. Are we good?
Yep.
Okay. So when I have an n by n matrix and I'm doing this Gaussian elimination process, that takes me order n cubed operations. And basically, eliminating this first row takes me n squared operations because I have to do n operations per row to zero out these entries under the pivot. And then it takes me sort of an n minus 1 squared and so on. And I sum that up to get my n cubed operations here. And that's fine when n is 3. And it's even tolerable when n is 5 or 10. But that's really a problem with these high resolution simulations that we're doing when n is a million or a billion or something on that scale. And so the real question that I want to ask is not just how do we solve AX equals B, but how do we do it when A comes from one of these discretizations of a PDE, which means it's going to be large. Millions are sort of the smallest size problems we really like to solve these days. It's going to be sparse. The way I do these discretization procedures gives me sort of a fixed number of non-zeros per row. The problems I'm going to talk about today have, 5 or 10 non-zeros per row in the matrix. More serious systems maybe have 100 non-zeros per row in the matrix, but still not that many. And I'm going to inherit properties from the continuum PDE. I might inherit symmetry or positive definiteness or other sorts of properties, depending on how I discretize, of course, whether I preserve those properties. And I only need an approximate solution is the other thing. Excuse me. I'm discretizing the PDE. I'm already introducing approximations. And so I'm only going to look for approximate solutions of these linear systems. Gaussian elimination gives me an exact solution, at least in exact arithmetic. And so I also want methods that allow me to tune the accuracy with which I'm solving these systems, just to avoid unnecessary expense in over-resolving an approximation. And so a big focus of my research over the last 20 years or so has been looking for these sorts of specialized techniques. They take advantage of matrix structure, and in the end, they need to be faster than Gaussian elimination. They need to be substantially faster than Gaussian elimination, particularly as we tackle these sort of complex heterogeneous 3D PDEs. Now, one of the ideas that we use here, and the one that I'm really going to talk about the construction of these methods, is preconditioning. And at its simplest level, preconditioning just means that the solution of AX equals B is also the solution of a lot of other linear systems, and maybe we should solve one of those instead. And so I can consider solving m times a times x equals m times b, or a times m times y equals b. Both of these are possibilities. And if m times a or a times m have nicer properties than a does, then it's actually substantially easier for me to try and solve, say, this system than it is for me to try to solve ax equals b. And that's the game that we play, is trying to find a matrix M such that solving max equals mb is an easier thing to do. Now, again, we're not going to apply Gaussian elimination to m times a. What we're going to do instead is use iterative methods here. And so we want to say that I have some approximation in hand, I'll call it x naught, to the solution of ax equals b, that is a inverse b. And I want to introduce some measure of the error in that approximation. And something that I have that's computable is just the difference between b and a applied to x naught. So that's a nice thing that I can always compute. We call that the residual. And what it is really is it's a applied to the error. So that just because it's a linear problem, b is a times x, this residual is a applied to the error. And so a simple, we call it a iterative method, a simple iteration for improving that guess x naught is to take that residual, take some weight, omega naught times that residual, add it to x naught to get x1. And we do this again and again and again. And if we're thinking about the preconditioned iteration, we just put m's everywhere. And we say, here I have m times the residual, that's m times a times the error. And my update takes the form of x naught plus a weight times m times that residual. And if I want to ask how does that do as an iteration, I maybe look at its error propagation form. And I see that how that does as an iteration sort of depends on this matrix here, identity minus weight times m times a. And I can chain multiple steps of this together. So I can do a second step with a new weight maybe. And that just gives me this now polynomial in m times a. We call these polynomial iterative methods because of this structure. And I do it again and again and again. And at the case step, I have a polynomial of degree k in m times a. This sub-zero here says that it has the property that the lowest order term in that polynomial is always the identity matrix, or a 1 if I think of it as a polynomial on the complex numbers. And now there's sort of a whole industry on how do we pick those coefficients, those omegas, in order to get good convergence out of here. Lots of different ways. You might fix them all to be the same and have a uniform or a stationary method. You might do something involving a Chebyshev polynomial and looking at the field of values of that matrix m times a. Or you might use Krylov methods where we sort of choose these polynomials for some sort of optimality. Conjugate gradient, GMRes, BiCGSAB, all of these methods are in this category. And the success of these approaches really just depends entirely on some measure of closeness between m and the inverse of a. And the argument here is that if m is exactly a inverse, if I go back up here, if M is exactly A inverse, then this preconditioned residual is exactly the error. And if I pick a weight of 1, I get exactly the solution after one step. And how M times A differs from the identity is what really controls the convergence of these schemes.
Can I interrupt,
And so-
Scott, for a second?
Yes, please.
So you're assuming, like, you from your problem, A will be invertible?
Yes, yes, I am always sitting in the world of square matrices, and they're either invertible or they have sort of very trivial null spaces that I know.
Okay.
And so this is sort of the structure of the PDEs that we're solving, is that those PDEs are always sort of invertible in the continuum setting, and we discretize them in such a way that the linear systems that we get out are also invertible at the discrete setting.
Okay, thanks. Thank you.
No worries. Other questions while we're stopped? All right. So how do I choose M is sort of the question that we really need to get at here, and what am I going to do? Well, let's recognize first of all that some systems are easy to solve, and we might learn something about how we can choose these preconditioners by looking at those cases and asking what makes them easy to solve. And here's a linear system that I think is easy to solve. I think, everybody I teach linear algebra to would love to see a problem like this on their final exam. And this is just a lower bidiagonal matrix, right? And so I solve the first equation for x1. It's just b1 over a11. And then I can use that value of x1 to solve for x2, use that value of x2 to solve for x3, and so on down the line. And so here's a case where sort of my standard forward solve in Gaussian elimination gives me the answer. It costs me 3 floating point operations per degree of freedom, and it's an optimal algorithm. It's sort of an order n algorithm. I'm going to look at a slightly different way of solving this because this opens up a class of methods for me. And that method is the method of cyclic reduction. And so when I think about it in terms of that lower bidiagonal system, here's the formula that determines the kth entry in that vector if I know the k minus first entry. And it's just that I update my right-hand side. I take the kth value of the right-hand side. I subtract the subdiagonal entry times the previous one, and I divide through by the diagonal. But I can chain those two things together and say this xk minus 1 is itself determined by the same formula, just referring now to xk minus 2. And then if I put that in and I push things around, I can recognize this as that same forward solve, but now with a stride of length 2, with sort of a modified matrix A tilde and a modified right-hand side B tilde. And so, for example, now if you give me x1, I could use this modified iteration to solve for all of the odd indices, and then I could go back to my original form of the system and solve for all of the even indices as well. In a matrix view of this operation, what I'm doing is I'm reordering my matrix into its even and its odd indices. And I'm saying that I'm going to look at the submatrix that tells me how the even indices talk to the even indices. The submatrix that tells me how the odd indices talk to the odd indices. And then I have these off-diagonal blocks that tell me how odd entries in X talks to even entries in X, and vice versa. And that system, that system down here that I'm sort of talking about using to solve for the odd indices first is nothing more than the Schur complement of this block form of the system. The system that I'm solving is exactly this one down here. And so I compute the Schur complement of this matrix into the odd degrees of freedom. I solve this modified system for the odd degrees of freedom, and then I can solve afterwards for the even degrees of freedom based on that solution for the odd degrees of freedom. And if I look at what I'm really doing in that matrix form, I'm actually doing a block factorization of that system. And that block factorization just comes down to here, and I do a block LU solve which means that I first solve for sort of an auxiliary variable that is just AE inverse times BE. That's what appears here. And then I solve a system with this Schur complement matrix S to get X naught. And then I solve another system involving AEE to get XE in terms of BE and X naught. And so there's sort of a system here that lets me go from the odd and even indices up here to solving for all of the odds and then all of the evens. And I can push that around and define that in terms of this block LU factorization. And I need two things for this to be an effective algorithm. One of the things that I need in doing this is I need that even subblocks of the matrix has not just sparsity itself, but a sparse inverse so that I can compute that Schur complement. And then I need to be able to solve systems with that Schur complement. I need to be able to solve for those odd degrees of freedom using that. In the bidiagonal example that we started with, AEE was diagonal, and S inherited a lot of the structure of the original bidiagonal system. And so this works really well. But of course, that's not practical, and this is a method that breaks down very quickly when we have more complicated matrix structures. And that's what we have in practical problems. So for example, here are a couple of grids from 2D problems that we solve. On the left, we're just thinking about, say, a structured grid, finite difference discretization. I have a 5-point stencil. At each point on this mesh, at each point where these grid lines cross, I have a degree of freedom, and it has relationships to its left and right and up and down. On the right, I have a picture of a mesh from a piecewise linear finite element discretization. And again, at each point of the mesh, I have non-zero entries in the matrix connecting degrees of freedom to all of the neighboring degrees of freedom on that graph. So that gives me a connectivity pattern that's much, much more complicated than these odd and even indices that I had for the problem that I started with. And so we need to generalize this a little bit, and we need to recognize that this cyclic reduction idea is very nice when it works, but it's not going to work perfectly for a lot of the problems that we're interested in. And that's where the idea of multigrid reduction comes in. I'm not going to talk too much about what multigrid is in this talk, but multigrid reduction modifies the cyclic reduction to bring in some ideas from the family of multigrid methods. And one way to sort of summarize multigrid reduction in a nutshell is to say whatever system you have, whatever the connectivity in that system you have, is separated into two sets of indices. We'll still call them even and odds for a second here. And then approximate the even to even submatrix by a diagonal matrix. So we're going to introduce a matrix approximation. And that lets me define a preconditioner, M, as the action of solving a modified system where I replace all of my AEEs with DEEs, that is the diagonal matrix that approximates AEE. And I replace my true Schur complement with some approximation of it. Maybe I form this by putting a D in here instead of an A. Maybe I form it in some other way. And this is sort of an old idea, it goes back to the 80s, and people have sort of looked at it in a few contexts since then. But a basic question is, does it work very well? And the answer is it works very well for a very limited class of problems. And that was sort of where some of the work in my PhD thesis and subsequently picked up. I'm going to change notation at this point because this odd and even notation is a little bit misleading unless we're solving the simplest of simple examples. And so I'm going to adopt notations where I say F and C, where previously I said E and O, and even and odd. And the idea is just to think about that Schur complement. That Schur complement is somehow a coarser representation of the original system that I was given. And you can think about having the original problem given to you on a fine grid. And the F points here are the pieces that I leave on the fine grid and I don't take to the Schur complement. And the degrees of freedom in C are going to be the degrees of freedom associated with this coarser representation. And so this line here defining M is exactly the same as what we just had. I'm just abandoning this even and odd notation. I feel bad changing notation, but sort of the idea of evens and odds only gets us so far, and it only gets us precisely to this point. In this notation, the MGR iteration sort of looks like this, which is if you give me that initial approximation, I generate my next approximation sort of in these stages. So the first thing I do is I compute a residual over the F points now. And then I do a stationary iteration to improve my F approximation using DFF as an approximation to AFF, or DFF inverse in particular, approximating AFF inverse here. I use that to write down a Schur complement system, an approximate Schur complement system. I'm going to solve for a variable I'm going to call YC. It's really the correction to XC. And again, that's based on sort of an updated value of the residual over those course grid points. And then I update both my F and my C points based on YC. And the F point update, again, depends on DFF. And the C point update is just a direct correction. This is the stationary iteration that corresponds to that matrix M that we define using that block solve. And I can write it in terms of its error propagation, that I minus MA or minus omega MA that we sort of talked about before. Now I see it as coming from two separate pieces. This first piece here is really this first piece up here that says former residual and update just the F points. We call this F relaxation for that reason. And this second piece here we call a course grid correction, and it says form a new residual, restrict it to the course grid just by sampling it at those C points, solve a system with the Schur complement or the approximate Schur complement, and then interpolate a correction with the blocks of this interpolation operator being given by these two pieces down here, an identity over the C and minus DFF inverse AFC up here. And it's this matrix that I want to analyze to get a sense of how well these methods work. And it's this matrix that I'm going to try and improve by using these machine learning techniques. It's in fact the division of degrees of freedom into F and C where the machine learning techniques are going to come in just a moment here. In my thesis work, we extended this and sort of made three specific changes. First of all, we added a relaxation weight to that F relaxation step that just adds a sigma to here. We replaced that restriction that had the form of zero identity by the transpose of interpolation, and we fixed a specific approximation of the Schur complement to be this Galerkin product, P transpose times A times P. And there are reasons for doing all of that from a multi-grid perspective. But the other reason that you might want to do that is because it lets you prove a convergence theorem. It lets you say something about how good these methods are. And in particular, if A is symmetric and positive definite, and I look at that matrix AFF and I can separate it into two pieces. It doesn't have to be this way, but you can think of it as a diagonal approximation to AFF and a piece that's left over. Under some conditions on those pieces, I can get a bound on the stationary iteration convergence factor measured in the A norm that's strictly less than 1. And that bound depends precisely on this value epsilon that appears in these conditions. And that's basically a size measure that tells us how big DFF is in comparison to E. And so a small epsilon says that DFF is very large in comparison to E. And a small epsilon gives me a very good convergence bound down here. Smaller epsilon makes this smaller. And so the key to success in doing that is sort of finding this partitioning where we can ensure that AFF is well approximated by a DFF, and that's a DFF that we're willing to invert and work with. So it has a sparse inverse as our typical requirement. We also want to make sure that we do that in such a way that the C set, the complement of this F set that we're approximating, is very, very small so we can afford to work with that Schur complement or that approximate Schur complement S hat. And in that original work that we did, we just used pure geometry to make those choices. We worked on regular meshes and we did things like saying, let's just take alternate lines in that regular mesh to be F and C, or let's just take a lower resolution but still fully regular mesh to be our course grid. And we realized a little later on that we could actually write this out as a nice constrained optimization problem. That I want to maximize the set of F or minimize the size of C while I can still satisfy those conditions on the convergence theorem. And the hard one in particular is this one, that I want to have AFF being able to be written as a DFF plus an E, where I get that small epsilon parameter in there. And that constraint is the one that's sort of hard to guarantee in general. But there was an easier special case that occurs when A is diagonally dominant, and that's often the case, at least for sort of the simplest PDEs that we care to solve, because that diagonal dominance of AFF gives us a way of bounding epsilon. And we recognize also that if AFF was purely diagonal, then that's the special case where epsilon is equal to 0, and the special case where we really have this classical cyclic reduction. And so we need to find that DFF. And what we did is we said, given an FC partitioning, I can quantify how diagonally dominant AFF is by simply taking the ratio of its diagonal entry. I'll assume that that's positive, although I could put absolute values around here if I needed to, over the row sum in AFF. And so if this is equal to 1/2, I have a matrix that's diagonally dominant, but not strictly so. And if all of these theta i's are a little bit bigger than 1/2, then I have a strictly diagonally dominant submatrix AFF. And we proved that if A itself was diagonally dominant, and all of these theta i's were bigger than some theta, which itself was strictly larger than 1/2, then we had a prescription for that DFF based on the entries in AFF and theta. And we get an epsilon out of there that depends on that theta. And this epsilon you can think of as being sort of an order 10 parameter or something like that. So if theta is 0.55, then this is a 0.9 in the numerator and a 0.1 in the denominator, and epsilon is 9. So those are the sorts of numbers that we think about when we think about epsilon. And I know that's not sort of the small epsilon that you might be used to from teaching calculus or analysis or something like that, but that's a small value relative to the scale of values that it could be in this set. And here's where the machine learning tools start to come in, is that when A is diagonally dominant, I can get an optimal partitioning by solving this combinatorial optimization problem at the bottom here, that I want to maximize the size of my F set, which is sort of a sum of these decision variables F sub I, which are 1 if I is in the F set, subject to the constraint that every row in the F set is diagonally dominant by this parameter theta. I can rewrite this just a little bit to be able to recognize this as a 0-1 integer linear programming problem. And that's useful mostly from a theoretical perspective, because it tells me that it's actually an NP hard or an NP complete optimization problem. And so this is a hard combinatorial optimization problem, and I'm not going to be able to solve it just by some simple algorithm. And so in that work, 15 years ago, we said, well, solving NP complete problems is difficult, and so let's just write down a simple greedy algorithm where we basically pick points and add them to the C set one by one. We try and pick the worst points to make points in the C set. And then we look at their neighbors and we add their neighbors to the F set if they ever become sufficiently diagonally dominant. And this works, and we wrote some papers about it, but it was never very satisfying because we never had a sense of really how well this worked. And that's what we went back to try to revisit in the last couple of years. And so we sort of recognized that combinatorial structure to the optimization problem, and we said, greedy algorithms are really the tools of 15, 20 years ago. We have much better tools for this now. I mean, simulated annealing is also not a new tool, but simulated annealing is a well-established tool for these sorts of combinatorial optimization problems. But moreover, we have reinforcement learning and other tools from machine learning. And so we wanted to give those a try. And we recognized that to do that and to sort of say anything about how well these methods worked, we really needed to look for some special cases that let us assess the performance and compare against these older greedy algorithms. And so a couple of the things that we did that Tarek and Ali really pulled together here was to write down these sort of theorems that say, well, what does the optimal coarse grid look like for some of these settings? And so for a standard 5-point finite difference Laplacian, we're able to prove that the optimal fraction of points in the F set should be about 0.8, 4/5. So we really should be coarsening, about 20% of our points should be on the coarse grid when we take this nice regular fine grid problem. And when we do it using that greedy algorithm, we're very far away, so that we only get about 0.56 or 56% of our points left on the fine grid instead of 80%. So there's quite a big gap there. And that's a gap that we hope we can address with these other tools. For the finite element Laplacian, where you have diagonal connections and not just cardinal point connections, the optimal F fraction is a little bit smaller at 7/9, and the greedy algorithm does actually a lot better. It gets 0.75. So here we see there's maybe less of an opportunity to do better. And here we see that there's quite an opportunity to do better, and we'd like to know how much better we can do. So how did we do it? Well, we started by looking at simulated annealing. The basic idea of simulated annealing is to say, I want to explore an energy landscape via some set of random perturbations. And so for us, the state is going to be this FC partitioning. Which points go in that F set? Which points go in that C set? And the fitness function that I want to maximize, I'm just going to take to be the size of that F set. And we'll bring the constraints in just a moment. And the basic idea in simulated annealing is that I have a temperature to my system, and I have a decay rate of that temperature. Every time I take a step, my temperature is going to decrease by a multiplicative factor of alpha. And every time I guess a step that I want to take, I'm going to accept that step with a probability that's 1 if it improves my fitness function, and a probability that's sort of an exponential thing depending on the temperature T, if it doesn't improve my fitness function, if I stay the same or my fitness function gets a little bit worse. And so the ingredients here are that I have my current state and I have its fitness function, Z of F. I have a candidate state, a step I'd like to take, and its fitness function, Z tilde, which is just Z of F tilde. And I accept that step if F tilde is better in terms of my measure Z, or with this probability that starts probably close to 1 when my temperature is very high and decays close to 0 when my temperature gets very low. And the generic algorithm looks something like this. I initialize a random state F and an initial temperature T. And at every iteration, I randomly pick a neighbor state of F. I look at this probability function. I draw a random number. And if this inequality is satisfied, I take F tilde to be my new F. And I just keep doing this either for a fixed number of iterations or until some other condition is satisfied. The adaptations we had to make this work for us is we keep that fitness function that's just the basic fitness function, but we keep a little bit more information on the side. We track our best constraint satisfying state that's found. In this case, it's very hard to stay on the constraint satisfying manifold. And so we let ourselves go off of that manifold, but we keep track of the best results we encounter on the manifold. We have to define what it means to move from one state to a neighboring state. And so those neighboring states are just exchanging points from F and C. And we just do this in a simple way. We either move 1 point from F to C, 1 from C to F, or we do an exchange. And we do these 3 things with equal probability at every single step of our annealing algorithm. And the one critical thing that we found was to localize the annealing process. That is, if we try and do this on the entire system at once, we see that really degrades with problem size. There's just too many decisions to make. And even just things like drawing random points and things like that actually becomes expensive in this context. And so we break this up into subdomains. Maybe we do that geometrically, or maybe we do that using like a k-means type method, like a Lloyd aggregation. And then we sort of iterate in sweeps where we apply this simulated annealing approach on each subdomain, and we go back and we loop over the subdomain. So it's sort of like a classical Gauss-Seidel type iteration between subdomains. And it works. So here is a plot that sort of looks at different ways we might distribute work. On the x-axis here is looking at how we distribute our smooth or simulated annealing steps per degree of freedom per sweep on each of these subdomains. I'm looking at 2x2 subdomains on the top left, 3x3, 4x4, and 6x6. So these are on structured grid problems for the finite difference Laplacian. And then the different lines in these plots are just different numbers of total SI steps per DOF. And the black line at the top here is what the theory tells me should be the optimal, or the best that I can find by hand optimization for this F fraction, that is how many F points relative to the size of the domain. And that's up here just a little bit above 0.8 for this problem. And so what we find is that if we take very, very small subdomains, as we do in the top left here, 2x2 subdomains, they're just 4 degrees of freedom per subdomain, we get stuck. We sort of get stuck a little bit far from the optimum. And that's just because there's not enough local decisions to make in order to really make good progress. On the other extreme, if we take very, very large subdomains and we take very, very few total SA steps, especially when we take many per DOF, we just don't have enough work. We don't do enough work to get to the very best states. And there's sort of a sweet spot in between, both in terms of subdomain size and how we divide the work between these sweeps and all of these sorts of things. And it's a bit of a grind to sort of figure out where to be in these algorithmic parameters, but we figured it out. And you know, if I look at, say, now I'm looking at a subdomain shape on the left-hand graph here, and again, just sort of the best grids or the highest grids on the y-axis here. You know, you can see that if I now just increase the number of steps per DOF, as my subdomains get bigger, I get better and better results, but only if I invest more and more work. And that's sort of the summary of a lot of what we learned here, is just we have to do a lot of work in this annealing process to get very, very good approximations. And so here on the right-hand side, we're looking at, you know, the x-axis now being the number of SA steps per DOF. And you see that we're still making sort of noticeable improvements in our grids when we go from 50,000 to 100,000 to 2 million SA steps per DOF. We're actually getting noticeable changes in the quality of the coarse grids that we're generating. It says we're really, you know, we have to do a lot of work to get the very best results here. So we learned a lot of lessons from doing this study. We found that these bigger subdomains gave us better grids, but only when we did more work. We can get close to optimal. And, you know, these grids up here with, you know, 0.79, say, as our F fraction are substantially better than the grids we got before. They're just not as good as we can do if we put in more work. And so we get better grids than that greedy algorithm. We don't lose convergence. We can see what those grids look like, and these are both grids generated by some set of parameters from that previous experiment. And by and large, they look pretty good. They satisfy the constraints. And what you're looking for in these things is like spots like right here, where you have 2 or 3 grid points together. There's another spot over here. These are points where we have sort of a local non-optimal behavior. But overall, these sort of spread out the coarse grid points. They do what we want. And then if we scale this with grid size, we go bigger and bigger and bigger. Again, the black line here is sort of the best that we know how to do. The left-hand side here is looking at the finite difference case. The right-hand side is looking at the finite element case. And what we see is in the finite element case, sort of all of the things we try stay pretty much right on that best line that takes us to sort of that 7/9 F point fraction. And for the finite difference case, we definitely lose a bit of optimality as our problem sizes get bigger, but we're still sort of within a handful of % of the optimum and much, much better than the greedy algorithm ever gave us. But the bottom line is literally the bottom line here. This tends to be expensive. Our online time to sort of partition one of these grids, say a 32 by 32 grid, we measure this in hours. And in classical algorithms, we're used to measuring this in seconds or fractions of a second. So we were encouraged by these results because we were getting much, much better solutions to our optimization problems, but we were a little discouraged by how much work we had to do to get them. And so we said, well, maybe we can use tools really from reinforcement learning to try and solve this problem and exchange some of that online time for offline time, for training time for the network. And so in a reinforcement learning approach, what we do is we keep track of, again, those f sub i's that tell us if we are in the fine set or the coarse set. And we augment this with a second variable, v sub I, that tells us whether we're violating the constraint at a point in the f set. And so v sub I is 1 if fi is 1, and if we have the wrong side inequality here. Our state space for this reinforcement learning environment, the agent that we're going to train, is just the set of fi's and vi's. So that's 2n binary variables. Our action space is going to be the set of violating f nodes. And given a state, the next state that we're going to select would be one of those violating points that we make from an f point into a c point. And the reward function that we want to look at is overall, we just want to try and maximize minus the size of the C set, or that's the same as minimizing the size of the C set or maximizing the size of the F set. And so if we set up this learning environment, then we can say with certainty that if we had an optimal agent, then that would exactly solve the optimization problem that we're interested in. It would give us the smallest C set or the largest F set possible, such that we had no violations. And then we train a neural network. And so we're going to use a graph neural network agent. We're using a dueling architecture here. And so we have these topology-aware graph convolutional layers. And basically the way this works is that we're estimating two things. We're estimating a state value and a state action advantage. And this sets us up for these sort of dueling DQN approaches, where basically we have two outputs from our neural network, and we are able to sort of do some localization again here to be able to make good decisions on sort of the subdomain scale. We train our network on a bunch of piecewise linear finite element discretizations, and they're very, very small, and that's one of the important points here. We do very, very small convex triangular meshes, so order of a few tens of unknowns up to about 100 unknowns. And we can sort of prove that all of this training has sort of an order n complexity when we use subdomains where the node degree is independent of n, which is a reasonable assumption in our case. And then again, we turn it loose and we see what it does. And so we sort of see, here's that regular grid example again, and we see that the reinforcement learning approach produces for us a coarse grid that is much sparser than the coarse grid that was produced by, say, a greedy approach here. Also on unstructured triangulations, we again get sort of better, so sort of sparser coarse grids or denser F grids, if you will, with the reinforcement learning approach than the greedy approach from before. We do some performance studies, and so on the left-hand side here, I'm showing you sort of these regular grids. Again, around 0.8 is the best result we're expecting here. And you see here's the greedy that degrades with grid size. And our reinforcement learning approach does pretty well with grid size. Here's a point where we have sort of, our triangles are very, very small along the top and they get bigger down beneath. That's something that's typical, say, in grids for geophysics, where we have a lot of information near the surface of the Earth and we have sort of less information deeper in. And we see now the scale on this graph has changed, but we still see that we're sort of 10% better or a little more with the reinforcement learning approach compared to the greedy approach. And overall, we look at sort of two things here. One of which is we look at sort of the F fraction. And so this is a plot showing the greedy F fraction versus the reinforcement learning F fraction. And here, being in the upper left corner, says that reinforcement learning is doing better than the greedy algorithm, and where all of our data points are sitting up there. And some of our data points are really doing much, much better, and that's sort of this trend up here with increasing grid size for those regular grids. And some of it is sort of sitting sort of noticeably better, but sort of staying tangent to that x equals y line. And those are problems where we increase the aspect ratios of the cell. We make things sort of more and more anisotropic. And then on the right-hand side here, I'm showing effective convergence factors of the resulting method. And so here we're just confirming that, in fact, we're getting a benefit in terms of a lower cost to our method, but we're not sacrificing any convergence. And so again, most of our data is sitting in that upper left quadrant or upper left corner where we want it to be. Some of these problems are sitting a little more close to that middle line. And that's because the greedy algorithm converges slightly better because it's got slightly bigger coarse grids. And that's a known thing within multi-grid methods in this class. So the takeaway here was we can learn AMGR partitioning. It's more cost effective than simulated annealing in the sense that my training time is still on that order of hours, but my evaluation time, my online time is sort of on the order of seconds. And that's really what I wanted to say. So, I mean, preconditioners are important. I work on preconditioners sort of all the time, but a lot of the time what we do with preconditioners is very heuristic. And these AMGR methods give us a framework with at least some guarantees on convergence. They're not ideal, they're not perfect, but they do a lot for us. But in AMGR, we really are limited by this NP-complete optimization problem. And so we've been looking at these other approaches. They are effective approaches, they are expensive approaches that either offline or online time is still more than we'd like to pay. And that's why we're looking at sort of extending these approaches with new machine learning techniques and also extending them to broader classes of problems and preconditioners. So thank you very much.
Thanks a lot for this interesting talk. Any questions from the audience?
Hi, Scott.
Hey.
I really enjoy your talk. I think I learned something new here, and how you apply these approaches to these important problems from numerics. So sort of towards the end, you mentioned about the online offline time. Do you get a sense? Your idea here? Do you think you need to for different PDEs and different domains? Would you have to retrain your reinforcement learning neural network to come up with these good preconditioner, or is it general enough that if you train on a large number of them that it can work for a wide variety of problems?
So we did a very specific study, which is we looked at piecewise linear finite elements on planar graphs. So we looked at a wide variety of planar graphs, and I could show you other graphs than just sort of these families, but we looked at a lot of things where we looked at how does aspect ratio influence this? How does node degree influence this? How do all of these sorts of things? And what we found was that we could train a network once on these randomly generated graphs that may have had sort of some of these aspects and others, and it was actually unreasonably effective across a wide range of planar graphs. I 100% guarantee you that it would not be as effective if we went to non-planar graphs. So maybe things, I don't know, on surfaces probably would be still fine. But if you start thinking about three-dimensional discretization, so you start thinking about piecewise linears on tetrahedra instead of on triangles, or if you went to higher order finite elements or other things like that, right? The matrix structure for higher order finite elements is actually much, much worse than it is in these cases, because you lose a lot of the properties you like. You lose diagonal dominance, you lose M matrix properties and things like that. And so I think we were, I think stunned might be the right word. We were amazed that we sort of got as much generality as we did from this sort of, very affordable in some sense offline learning time. And this wasn't on a supercomputer or anything like this. This was just on a student's laptop. But I think that there's definitely limitations, and we haven't fully explored where that limitation ends. My guess is it would be somewhere in 3D or for more complicated finite element spaces in 2D. Yeah.
Thank you.
Thanks.
Jeff had another question.
Yes, this might be a bit naive, but I'm sort of wondering I guess, what am I trying to say here? How much importance do you think people working with these methods, relatively speaking, put on this kind of issue versus the quality of the linearization issues that you were sort of mentioning that you assumed were going to be true, or basically dealt with?
Right. So I think that's a great question. So in my part of the simulation world, we do a lot of Newton's method. And of course, with Newton's method, what you always worry about is the quality of your initial guess, right? How close are you to that root that you're trying to find? You also, of course, worry about whether or not there's only one root or whether you have multiple solutions to your nonlinear systems. And those are issues. So what we do for time-dependent problems, we actually have an advantage because we're moving from one time step to the next time step in these simulations. And the solution at the previous time step is a pretty good guess for the solution at the current time step. And so we often find in those sorts of cases, we have very good initial guesses, and Newton's method does exactly what we want it to do. I think what's harder is when we have sort of problems with exotic parameters. And I work with this in the setting of liquid crystals, for example, where we're interested in looking both at physical parameters, but also at geometric parameters. What happens as we change the domains we're looking at, or things like that. And you get, things like geometric frustration and other sorts of issues that come up there. And in those sorts of cases, the linearization is a bit harder, and we have techniques that we use, but certainly you run into issues where things like piecewise constant continuation and parameters and things like that doesn't work, and you have to do more sophisticated settings. So it's really an issue. I would say on the time-dependent problem side, we know what to do. And on the sort of steady state side, or sort of things like topology optimization and other sorts of problems, it's maybe a bit harder. There are techniques that people use, but they're not always guaranteed to work. And sometimes you do struggle a little bit with this.
Okay. Well, are there, I guess, when these methods are used, do you have any sense of whether or not the main emphasis is on trying to get the code to run efficiently via good approximations, or if it's equally important to worry about whether these approximations are taking you away from the original problem that you tried to solve?
So are you asking the question at the approximations that I'm making inside the construction of my preconditioners, or at the level of the discrete models that are approximating the mathematical models that are approximating reality?
The second case.
Okay. So we know, of course, all the time that when we write down PDE models of physical systems that we are neglecting things, and you get to choose to some extent what you want to include and what you don't want to include. And so things like incompressibility, right? Incompressibility is a convenient assumption, but not everything that we treat as being incompressible is truly incompressible. And I can point to a very real example of this, because this picture here comes from some work I did 10 years ago working on modeling mantle convection. So how does the rock inside of the Earth's mantle move, and how is that driven by thermal currents and so on? And this is a case where, of course, we can't do a laboratory experiment. We can't, make an Earth in the lab that does realistic things. And we can only take indirect measurements. So we really don't have good answers to what's going on down there. But this is what drives plate tectonics and what drives lots of things about the geophysical processes of the Earth. And when I started on this project, we really looked at this, and we were using an incompressibility assumption for the rock in the mantle. And that was motivated in part because even at low resolution, they couldn't solve the problem. And so they had something on the order, I can't remember anymore, but I think it was sort of something on the order of 10-kilometer or larger meshing within the mantle. And at that scale, compressibility effects were not important. We improved the model. We got them down to sub 10-kilometer scale models in the mantle. And at that scale, compressibility was important. And so, in fact, my involvement in this project stopped around these last papers in 2010, 2011, because the group that I was working with had to go back to the drawing board and figure out how to incorporate compressibility into the PDEs in a way that gave them physical results. So what were the mechanisms for compressibility? How did they depend on temperature? How did they depend on other variables? What did they need to figure out in order to do that? And there was sort of a period, I mean, it's over now, but there was a period of 3 or 4 or 5 years where there weren't a lot of new papers on simulation in mantle convection because there were a lot of theoretical papers asking the question, what's the right model now that we can simulate at, say, 1 kilometer scale? And that's where, you know, this diagram gets messy. Never do you have a physicist or an engineer walk into your office and say, here is the problem I want to understand. Here is the perfect mathematical model for that problem. And here is the data that I would like to have to answer my question, right? You know, it's a much messier process. And they walk in and they sort of say, oh, I want to understand this. And then you try and answer that question, and then you give them an answer to the question you think they asked, and they say, oh, that's not the question I wanted to ask, and you keep going. But you know that you're making mistakes in that. You know, in this sort of part from here, you know that you're always making mistakes in every one of those steps. And the question is whether or not they are justifiable, whether or not the things that you are neglecting are neglectable at the resolution that you're answering the question.
Okay.
Other questions? Or maybe in the meanwhile, I will ask a question. So the grids that you showed us, are they, I mean, I think like in standard machine learning, there is a lot of randomness, right? Like how you
Yes.
solve the optimization problem. Like, are these grids, do they always come up looking like this? Or like how stable are these sort of
Right.
patterns that you showed us? Yeah, in particular, this one, for example.
Right. So here you can see these are 2 calculations done sort of between 4x4 and 6x6 subdomains, right? And what you see is there's actually sort of structures here where you have sort of, you know, on the left-hand figure, you have sort of 2 points, and then you have this offset of 2 points down below. And you see that structure, say, here and here repeated, right? So you see micro scale pieces where you have sort of repeated structure, but the macro scale is certainly not sort of constantly repeated. And so I don't remember the numbers exactly. I think the point on the graph on the right here, I believe, has 2 more F points than the graph on the left. So these are basically equally good approximations. They're within a fraction of a percent of one another to the optimum. But they look visually different, right? And part of that is just the way they were calculated. But, you know, when you look sort of at any one region, you see, you know, pieces where you almost have structure. You see these sort of not quite diagonal lines coming up on the left. You see hallmarks of that on the right, but the slopes are different. They're sort of rotated 90 degrees or things like that, or there's pieces like that. And then when we did it again using RL, you know, we sort of have them going a bit the other way. So there's maybe, I don't know what the word is. There's structure that you see emerging from here, but it's never seeded the same way. And that we certainly see the impact of random seeding and things like that. And all of these, we can reliably reproduce good quality approximations, but they are never the same. They're not, you know, perfectly reproducible because there's always this stochastic component.
Maybe a quick sort of follow-up question. Can you show the results for reinforcement learning, like as a function, like the quality or a fraction as a function of the previous one?
Yeah.
So you have to train a new agent for each new grid size, or is that
No, that's the we actually we train the agent on sort of a very small, well, a very large set of very small problems. So I didn't write it down, but there's quite a large set of these problems. I think 10,000 randomly generated triangular meshes or something like that. They're small. They're on the order of a few tens of nodes. And the reason that they're small is because this is going to be the size. We're going to do the same sort of subdomain thing here. We do it algebraically. You hand me the big matrix you want to solve, and then we have it's like a k-means type algorithm that separates it out into subdomains. And each of those subdomains is sort of this size or smaller, this 30 to 120 or smaller. You know, we often deal with these as being sort of 40 or 50 nodes or something like that. And so we train on a bunch of small problems that are the size of our subdomain problems or a little bit bigger. And we just throw down piecewise linear finite element discretizations on those problems. And that's what we use in our training set. And we train once and then we apply it to the whole set of test problems. So here, for example, for the regular grids, we went up to a grid size of sort of 50,000. For some of these other classes, we only went up to grid size of 2,500 or something like that, but still much, much bigger than the size of any single problem in our training set.
So how large is your state space then, right? If you go back to this formulation of the, I guess, reinforcement learning problem, right? It is 2 to the power of n, something like this. So how large, how large is your state space then for the problem that you train it on?
So yeah, we have 2 binary degrees of freedom for every node in the mesh, right? And so it's 2 to the power of 2n. It's not quite that because, well, it's more or less that, right? If fi is 0, then vi doesn't matter anymore. But say 2 to the power of 2n. And so even at 30, right, that's 2 to the 60. And so what is that? That's 10 to the 18 or something like that, right?
Yeah, so you get you get really large spaces. Yeah, that makes sense. Even for these small problems. Yeah, fair enough.
Yeah.
And you never encountered any instability with your Q learning? Because Q learning is notoriously sort of famous for instability on training.
I won't say never. And I would have to ask Ali in particular. So we did some study of different ways of training this network and things like that. And I think we found that the advantages of these DQN methods made them sort of worth putting up with any of their foibles. So we did try and do this in other ways, and we really found that, in particular, this sort of, this state action advantage idea, right? This piece and sort of trying to train on learning that was critical to us in making this complexity argument here that, that both our training and in the end our evaluation were going to be sort of order n processes, and so that we weren't going to sort of have any step in here that was sublinear complexity. And that's sort of the world that I spend a lot of my time in. Is you're never willing to invest even quadratic cost in one of these algorithms. It's always got to be linear.
Okay, well, thank you very much. Any other questions? If there is no more question, then thanks again, Scott, for this really interesting talk. There will be another seminar next week, maybe not quite the same time. It depends a little bit on the speaker, but there should be an announcement coming out soon. So do watch out for this if there is a slight change in time on the seminar, but there will be a seminar next Tuesday. Yeah, and thanks everyone for showing up, and I'll see you next time.
Great. Thanks, everyone.
Thanks, Joe.